Welcome to qnawire.
Hey guys, let's do problem 99. In this problem we need to calculate the volumetric flow rate of the gas and the required volume of catalyst bead. We know carbon monoxide and hydrogen reacts to give us methanol, and in this problem the reactor is designed to produce 54.5 kilomole per hour of product, which is methanol, and 25% of conversion took place. Therefore, the amount of carbon monoxide that must be fed to the reactor is the number of moles of methanol divided by the conversion factor. The reason behind this is because 1 mole of carbon monoxide is producing 1 mole of methanol. Therefore, the stoichiometric ratios are same. Therefore, the number of moles will be the same. Now, number of moles for methanol is 54.5 kilomole per hour, and 25% of conversion took place. Therefore, we need to divide it by 0.25, and we get 218 kilomole per hour as the amount of carbon monoxide, and the molar rate of hydrogen is then 2 multiplied by number of moles of methanol divided by the conversion factor. The reason is 2 moles of hydrogen gives 1 mole of methanol. Therefore, the number of moles for hydrogen is double. 2 multiplied by 54.5 kilomole per hour divided by 0.25, and we get 436 kilomole per hour. So 218 kilomole per hour carbon monoxide and 436 kilomole hydrogen was fed into the tank. Therefore, the total amount of gas fed into the tank is is 218 plus 436 kilomole per hour, or 654 kilomole per hour. Now, the critical temperature and pressure of hydrogen and carbon monoxide we need to find. For carbon monoxide, the critical temperature is 133 Kelvin, and the critical pressure is 34.5 atmospheric pressure. And for hydrogen, with Newton's correction, the critical temperature is 33 plus 8 Kelvin, which gives us 41 Kelvin, and the critical pressure is 12.8 plus 8 atmospheric pressure, which is 20.8 atmospheric pressure. Now, let us calculate the pseudo-critical temperature. The mole fraction for hydrogen is 2/3, and that for carbon monoxide is 1/3. Therefore, the pseudo-critical temperature is 71.7 Kelvin, and similarly pseudo-critical pressure critical pressure is 25.4 atmospheric pressure. Now, let us calculate the pseudo-reduced temperature and pressure. The pseudo-reduced temperature is the process temperature divided by the pseudo-critical temperature. Process temperature is 644 Kelvin. Therefore, pseudo-reduced temperature is 8.98, and pseudo-reduced pressure is process pressure divided by the pseudo-critical pressure. Here we get the given pressure for the system is 34.5 megapascal. Let's convert it to atmospheric pressure. Therefore, 34.5 megapascal multiplied by 1 atmospheric pressure divided by 0.101325 megapascal, and we need to divide it by the critical temperature, which is 25.4 atmospheric pressure, and we get the pseudo-reduced pressure as 13.4. Now at this pseudo-reduced temperature and pseudo-reduced pressure, the Z factor is 1.18. Now we can calculate the volume of gas using the compressibility factor equation of distillate. Therefore, the volume of gas necessary is the Z factor multiplied by number of moles of gas, RT, divided by pressure volume divided by the pressure. And the pressure of the system is 34.5 megapascal. Let's convert it to Pascal by multiplying 10 to the power 6. Therefore, we get the volume of the gas necessary is 120 meter cube per hour. Now we need to calculate the volume of the bead. Volume of catalyst bead is the volume of gas needed divided by the catalyst bead volume per hour, or 120 meter cube per hour divided by 25,000 meter cube per hour. Per 1 meter cube catalyst bead. Which gets the volume of catalyst bead is 0.0048 meter cube catalyst. Next, we need to calculate what is the volume flow rate if methanol is completely recovered. Now all the gases that do not react to create 54.5 kilomole per hour of methanol would be recycled, and therefore the amount of fresh bead is the number of the moles of methanol produced multiplied by the stoichiometric ratio. Let's write it down. Therefore, the number of moles of carbon monoxide which reacted is number of moles of methanol. This will be the same, which is 54.5 kilomole per hour. Number of moles of hydrogen reacted is equal to 2 multiplied by number of moles of methanol, which is 2 multiplied by 54.5 kilomole per hour, or 109 kilomole per hour, and the total number of gas reacted is 54 plus 109 kilomole per hour, which is 163.5 kilomole per hour. Then the fresh volumetric feed of gas is Z factor multiplied by the number of moles of gas, RT, divided by pressure. Let's insert all the values. 1.18 multiplied by the gas constant multiplied by the number of moles, which is 163.5 multiplied by 10 cube mole per hour. Gas constant is 8.314 meter cube Pascal mole inverse 1 Kelvin inverse 1. Temperature is 644 Kelvin, and the pressure is 34.5 megapascal. Let's convert it to Pascal by multiplying 10 to the power 6. Therefore, we get the fresh volumetric feed rate of gas is 29.9 meter cube per hour, which as expected is 25% of the originally calculated volume and matches the single phase conversion percentage.